Hello, everyone. Welcome to today's edition of our extreme and probabilistic combinatorics webinar. Before we start with our speaker, let me quickly go through some technical stuff. As you probably all know, this talk is being recorded and will be posted on YouTube. So please bear that in mind if you are asking questions. It will appear on the internet at some moment. Our speaker sent me his slides. So if you miss a definition or something and you need to check the slides, then you can find them on the webinar webpage. If you have any questions, please ask them primarily in the chat, and I will be following the chat, and in case it, the question is not answered by any other attendee, then of course I will stop the speaker, and we think that that's the most efficient way to run this. Of course, there will be then time for questions at the end, and there will be a sort of a second round for questions at the end, and the second round will be not recorded. So if you prefer to ask a question which is not recorded, then there will be an option for that as well. Okay, so now it's my pleasure to introduce Joonkyung Lee from the University of Hamburg, and he will be talking about commonality in graphs. Please.
Right, thanks for the invitation and the introduction. So yeah, I'm going to talk about something about common graphs. Okay, so if you do have questions, then just stop me whenever you want. Yeah, so the time will be sufficient, I guess. Okay, so let me start by this classical result by Ramsey, which almost everyone here would know. So let me just state it in a rather qualitative way, which is the following. So given any two-edge coloring of a sufficiently large complete graph Kn, there always exists a monochromatic copy of a fixed graph H. So whenever my large N is large compared to my fixed graph H, then I can always find the monochromatic copy whenever I two-edge color my Kn. Okay, then the next natural question would be, if exist, then how many? So this question can be formalized by the following terminology. So the TH of G is the normalized number of H copies in G. So here I use this normalized homomorphism density, but yeah, but it's essentially the same because we can easily argue that the both colors are dense, which guarantees that the homomorphism counts are same as the injective counts and so on. So, but let me just stick to this TH of G for this talk. And the Ramsey multiplicity constant C of H is defined by the minimum number of my H in G and the G complement whenever my G is an n vertex graph, and I take the minimum, take the limit as n tends to infinity. So here G means the red graph, red subgraph of Kn, and you can think of G bar, which is a complement of G, as a blue subgraph of Kn. So this really asks the minimum number of H, which is monochromatic in this two-edge coloring. Okay, and we say that my H is common if I have this equality. So the minimum number is 2 to the 1 minus the number of edges in H, which means the minimum is attained by the random two-edge coloring. So here, random two-edge coloring means I flip a fair coin to decide whether to color this edge with red or blue, okay? So this is a definition. And let me give you some examples. So here's Goodman's formula, which is one of the important elementary results in the area. So it can be rephrased as follows. So here I have these monochromatic triangle counts, and here I have monochromatic two-edge counts. So here P2 means the two-edge path. Okay, so I have this formula, and you could actually prove this by yourself quite easily. So let me just skip that. But let me just show you some consequences of this Goodman's formula. So it is, again, probably easier than Goodman's formula itself. So again, it's easy to prove that monochromatic copies of two-edge path is at least half, if normalized. So let me just give you a short proof for this. So let my rho of x to be the expectation of, so gxy is the indicator of my graph G, where x and y are the randomly sampled vertices in G. So I put 1 if there is an edge and put 0 if not. Okay, and then I integrate this guy with my y. Then what I have is essentially the normalized degree. So the vertex degree at x normalized by the number of vertices in G. Okay, that's my rho. And I can compute my two-edge path as follows. So this is nothing but this expectation, because I want my x and y are adjacent and x and z are again adjacent. So if I then integrate this function by z and y respectively, and then I have expectation rho of x squared, and then I apply convexity, which is expectation rho x total squared, and hence this is p squared, where p is the edge density in my graph G. So everything's clear so far? Yeah. Then I do have the same formula for my complement of G. So which gives the following inequality, p squared plus 1 plus p squared. And it's very elementary to see that this is lower bounded by a half. And this proves that the path of length 2 is common. And moreover, by Goodman's formula, we can just plug that in into here. And that gives a lower bound of quarter. And hence, my triangle, the triangle is common. Okay, more generally, every odd cycle is common, but this is already quite non-trivial. So this is an old theorem by Sidorenko. And this is strong enough to, in particular, imply the Erdős-Stone theorem for odd cycles. So you can basically prove Erdős-Stone theorem by assuming the commonality of an odd cycle. And moreover, there's a sparse pseudo-random analog using this argument too, which is by myself with Søren Berger and Matthias Schacht. Yeah, so this is just over-citation of myself. Okay, and let me move on to this topic of common graphs more directly. So here's a famous conjecture by Erdős, and which is later generalized by Burr and Rosta. So Erdős conjectured, because of the Goodman's formula, he just conjectured that every complete graph must be common. And Burr and Rosta later generalized that every graph H is common. And both conjectures are disproved. Firstly, Burr and Rosta's conjecture was disproved by Sidorenko. He proved that a triangle plus a pendant edge is not common. And then Thomason, at roughly the same time, disproved Erdős conjecture by proving that every KR, whenever R is at least 4, is not common. And later on, Jagger, Šťovíček, and Thomason proved that any G containing K4 is not common. And there are worse non-bipartite examples that have been found so far. For example, Jacob Fox, this is one of the earliest results by Jacob. He proved that given any chromatic number at least 3, which means the graph is non-bipartite. And then there exists some kappa of, some kappa that depends on this chromatic number, such that there exists a graph H with that chromatic number chi, and the Ramsey multiplicity constant for H is exponentially smaller than the conjecture bound half to the 1 minus, so half to the number of edges minus 1. Yeah. So it could be exponentially worse too. So these are what's known on sort of negative side. And here are some positive results, which means there are some common graphs. So here's a famous conjecture by Erdős and Sidorenko, which is often cited as Sidorenko's conjecture. So whenever H is bipartite, then given any graph G, I have this inequality over here. So this essentially means that my H count is lower bounded by the edge density to the number of edges in H. And there's a simple argument by using this inequality that shows that whenever H satisfies the conjecture, then H is common. So here's the argument. So here I again use P for the edge density of G, and hence 1 minus P is the edge density for the complement. Yeah, so then I have this lower bound, and it's essentially the same argument. You could actually it's quite easy to prove this inequality over here by using convexity. Okay, so we have H being common whenever H satisfies the conjecture. And yeah, if I take the contrapositive of this argument, then if a bipartite uncommon graph H exists, then it must violate this inequality. And hence, if I find the bipartite uncommon graph, then I disprove Sidorenko's conjecture. But Sidorenko's conjecture still remains open, so which means we have no bipartite uncommon graph so far. And moreover, every bipartite common graph satisfies this inequality over here, which means for bipartite case, we are totally relying on the progress on Sidorenko's conjecture. Yeah, so it would be interesting to see if there's an example bipartite graph that's common but unknown to satisfy Sidorenko's conjecture. But no such example exists so far. And there are many recent results, some of them due to myself with colleagues, but let me just focus on the non-bipartite case for this talk. Okay, so here are some lists of non-bipartite common graphs. So by Goodman's formula, we do know that triangles are common. And this was generalized by Sidorenko for odd cycles. And he also proved that these graphs, this is so-called triangle vertex tree. So you can just recursively define this by adding a triangle to it. Yeah, and the intersection between the existing part and the new triangle is just a vertex. So this is so-called triangle vertex tree. And the triangle edge tree. So here the intersections of triangles are always an edge. So this is another example. So he proved that those are common. And some more, which I would talk about later. Okay, and then Jagger, Šťovíček, and Thomason reproved these results. And they also proved that even wheels are common. So this is in fact contained in this ... part, which I'm going to talk about later. Yeah, but they gave a little bit simpler proof, yeah, and so on. And after that, it has seen almost no progress before, before the invention of flag algebras. So by using these Rasborov flag algebras, these 5 people, Tommy, Hladky, Král, Noreen, Rasborov, prove that this particular graph of 5 wheel is common. And yeah, so this is the question by Jagger, Šťovíček, and Thomason. So they ask, this graph is particularly common because it's a 4-chromatic graph, but has no K4 in it. So, and so far, I think, as far as I know, this is the only example that's common, but has no K4 inside, with chromatic number larger than 3. And here's another example. So these two people, Hurst and Raghuvanshi, prove that this particular graph, which is so-called house, is common. So they also use flag algebra. So this was a high school or undergrad research project pursued at MIT. So Raghuvanshi, I think, was an undergrad. Yeah, and James Hurst was a graduate student there. Yeah, so these two examples depend on flag algebras, and the other bipartite examples rely on the progress on Sidorenko's conjecture, and there have been almost nothing except these. So before moving into the results of ours, let me just give you 1 minute Cauchy-Schwarz class. So here's my graph H. Suppose it can be decomposed in such a way that there are 2 subgraphs J, which are isomorphic, and then they intersect on the subgraph called K, and there's an automorphism in my H that maps this left J to right J while fixed K. So this is my graph. And I also want, if I delete my graph K, then my H is disconnected. So this is a basic setting. So if I delete this, then there's, the graph will be disconnected into 2 or more isomorphic pieces. And then I have this inequality. So if you've ever applied these Cauchy-Schwarz on the graph counts, then you would probably understand what I mean. And yeah, it's not hard to prove this inequality by just using Cauchy-Schwarz. For example, let D be a diamond, which means K4 minus an edge, and let W4 be the 4-wheel, like this. So I add this apex vertex to the 4 cycle, which is a tripartite graph. So otherwise it's, in other words, it's K1, 2, 2. This is a complete tripartite graph. Okay. Then what I see is these bunch of inequalities. So you've seen this inequality and the proof already. And here the same kind of inequality gives that the 4 cycle is lower bounded by the 2-edge path squared. And here's another inequality. So here are 2 copies of triangles which are glued together along one edge. So I divide one edge out, like the K here. And here's another graph, the 4-wheel, which can be lower bound by the diamond square, because here's a left copy of diamond and the right copy. Then I glue these together along this path of length 2. So this is what I get. Okay, so these are a bunch of inequalities that we can easily obtain. And this Cauchy-Schwarz calculus extends in a tree-like way by the theorem of myself. So let's call this particular graph a fish. So because it looks like fish. So then my graph is lower bounded by the triangle squared by the edge density, because I basically glued 3 triangles. So here are 3 triangles along an edge and a vertex. So the vertex count is always 1. So I just omitted that count, and this is an inequality. And this extends in a tree-like way, in a similar way. Okay, so let's see the proof for this theorem. So this is our theorem. So every triangle tree is common. In particular, this fish is common. And this particular graph was a question by Jagger, Šťovíček, and Thomason. So they actually didn't know this particular graph is common or not, although they knew that this part, which is a triangle edge tree, and this part, which is a triangle vertex tree, are common. So this answers their question. And the proof is 100% human. So there's no flag algebras involved, and moreover, it's quite simple. So let me just give you the proof for this particular case fish. Okay, here's a proof. So by using this information theoretic, so I forgot to mention that the inequality by myself follows from an information theoretic approach, which is essentially a bunch of entropy inequalities. So I can prove this inequality by entropy, or by just citing my inequality. And then I basically do nothing but pulling out these p's, p and 1 minus p's, okay? Then I get this number, and I apply the convexity of the square function, which is, in other words, just Cauchy-Schwarz. So I get this lower bound, and then I apply, again, some convexity of this function. And hence, I get the correct bound, which is 2 to the minus 7. Okay, this is pretty much the proof, and this extends for every triangle tree. So this is probably the simplest part of our theorem. And we get more and more things. For example, we prove that the octahedron, which is a complete tripartite graph, K222, is common. And the proof is, again, 100% human. So let me just give you a proof, sketch of the proof here. Okay, to that end, as a warm-up, let's prove that the full wheel is common. So full wheel was this graph over here, to recall. Okay, so note first that we just apply two Cauchy-Schwarz and two Cauchy-Schwarzes, and then we get this inequality over here. Okay, and then what we do is to deal with the denominator. So here we kind of know how to deal with these p's and 1 minus p's on denominator. We've just seen the way to deal with these guys, but we haven't seen how to deal with the passive length 2 counts. So these terms in denominators are always the main obstacle on applying this Cauchy-Schwarz calculus. But let me just rephrase this a little bit first. Okay, so let MH be the monochromatic copies of H in this 2H coloring. So this is my notation. So here it depends on the choice of my G, but let me just suppress that to simplify things a little bit. Okay, then what I have is this inequality. So here I just apply this inequality for G and G bar. And then I again did nothing but just pulling out these monochromatic 2H path counts. And then I use convexity. So see, these are, if this is Q, then this is just 1 minus Q, right? So I just use convexity of square, which is basically this. And yeah, and then I get this inequality, by again using some convexity. So we do know that we can deal with these kind of terms. Okay. So far so good. So what we've just proved is this inequality, which resembles the inequality follows from the usual Cauchy-Schwarz. And then what we'll do is to use Goodman's formula. So Goodman's formula proves that the monochromatic copies of 2H path is exactly interpreted in terms of the monochromatic triangles like this. And thus, I can use this to obtain a rational function in terms of the monochromatic triangles. Okay, this is a function, and it's a rational function that is increasing. So in particular, my monochromatic counts for triangles are at least a quarter. So this rational function must attain the minimum at that point. And the minimum is 2 to the minus 7. So we've just proved that this four-wheel is common. So this is exactly the way how Jagger, Šťovíček, and Thomason proved that the four-wheel, or in more general, any even wheels are common. Okay, so this is the proof, and let's prove this theorem of ours. By using this. Okay, so the first step is again Cauchy-Schwarz. So we have some bunch of Cauchy-Schwarz. So here, this octahedron K222 is obtained by attaching 2 copies of four wheels along this outer full cycle. So this is a Cauchy-Schwarz, and then I plug in this Cauchy-Schwarz bound again. Okay, so in a similar way, as you've just seen, I can just translate this in terms of the monochromatic copies by using some simple convexity argument. So this is the inequality we have. And well, we can still use the Goodman's formula to deal with these terms. But the term here, the monochromatic copies of full cycle, this has no Goodman's formula. So this is hard. So this is where all the difficulty lies. So we can deal with this, but we have no idea at first how to deal with this guy. But don't panic. Here's the way. So we can still prove that some inequality like this. So for some C positive. So a similar, an analogous inequality has also appeared in this work by Hatami, Hladky, Noreen, Rasborov, and Krall. Yeah, so they use this kind of inequality to obtain a stability result for these 5 wheels. So, but we're gonna prove by hand that this inequality holds for my diamond, which is a K4 minus an edge. Okay, so, and then we will gonna optimize the rational function as we did. So that's the plan. And here are some remarks. So firstly, one cannot use C that is very small because we have to optimize this rational function. So you'll see in a minute that we have to be, not in a minute, for some minutes. So you'll see anyway that this small c could cause a problem in this optimizing the rational function. And again, this inequality gives us some sort of stability results. So in particular, if my diamond counts is 1/16, which means it attains this commonality bound, then my graph must be random. The coloring must be a random coloring. Yeah, so these are 2 remarks, and let me just move on to the proof of this. So we're gonna prove this inequality with C being 1/7. So that's a plan. And to this end, we have to do a little bit of calculus, which means we expand this out. So here f means my indicator function for the graph G, and then I'm gonna replace my f by a function 1 plus G divided by 2. So here, f ranges, so the range of f here is the unit interval from 0 to 1. But by reparameterizing like this, I lose the non-negativity of f, but my g is still ranges from -1 to 1. So that's the thing. But I can simplify this a little bit as follows. So if I replace my f like this, then I get this equality by pulling out the half term. And then I expand this multilinear expression here to obtain this. So the odd, so here f ranges over all subgraphs of H, right? Yeah, and then I have this sum over here. So you could easily check, and you could have already seen this at somewhere. So basically, whenever you deal with commonality, there is a good chance that you just deal with this expression. Okay. Okay. So what I'm gonna do is to put the diamond for my graph H. Then I get this. So you can easily check this expression by hand because there are 4 copies of the triangle. So here K3 plus is a triangle plus a pendant edge, the Sidorenko's example being on common graph. So you have 4 copies of these in your diamonds, and there's 1 copy of full cycle, and there are 8 copies of passive length 2, and there are 2 copies of matchings, the 2 edge matchings. So this is it. And you could do the same with full cycle, which is actually simpler. So there's 1 copy of full cycle, which is an even subgraph of itself, and 4 copies of passive length 2, and 2 matchings. Okay. So these are just basic calculus. You can just easily check yourself. And from these, we obtain this expression over here. So if I subtract this lower equation from the upper one, then I get this. Okay, so what's the deal? Here's the deal. So given any g from the unit square to -1 to 1, which is a limit object, if you know something about these dense graph limits, and then the easy Cauchy-Schwarz inequality gives probably not as easy as those really easy examples, but still not very complicated. So we can bound these signed K3 plus counts by the passive length 2 and the full cycle square root. So this is some Cauchy-Schwarz that you can handle. And then because of this inequality, whenever the geometric mean of these 2 quotients dominates 2 times the quotient over here, then we have a sum of squares. And we do know that for the rest of terms, for example, this guy is non-negative and this guy is non-negative and these guys non-negative. So we only have to care about this guy, and that's handled by this inequality once we have this inequality. Okay, so far so good. So we've just proved this inequality, and here's a way of using it. Here's a way of using it. Okay, so if I plug this bound into my diamond counts, and then I have this, well, I can still express everything in terms of the full cycle, because the monochromatic full cycle is at least the monochromatic passive length 2 squared. Okay, so I just plug that in and I get this rational function, which doesn't work. So if you do some calculus here, then it's easy to see that it attains a minimum at 5/16, which is larger than 1/8. So this particular approach doesn't work. So this means that even if you have a correct inequality that can work, you have to be careful. So this optimization of a rational function is quite subtle, that even if you have the right inequality to apply, if you apply it in a slopey way, then it fails. So here's a correct way of using it. So instead we use firstly Goodman's formula. So this is Goodman's formula, and here it's just a Cauchy-Schwarz. So the diamond counts is at least the K monochromatic counts squared. Okay, so this is my so this is Goodman's formula. Okay, and then I do this calculus. So, and then I have this rational function. Yeah, so, and this particular rational function attains a minimum at this value, which is slightly smaller than 1/16. And hence I can argue that because my diamonds are common, this rational function attains a minimum at 1/16, which gives the correct bound for the monochromatic copies of the octahedron. So this is the correct argument of using it. So yeah, we're somehow walking on a very thin ice, but in this particular case, we succeeded in proving the right bound. Okay, so this is the way, and we obtained this theorem. And if we use the help of flag algebras, which gives us a tighter inequality that's analogous to this diamond versus full cycle inequality, then it also proves the following. So given any a plus b at most 7, every k a b t is common. In fact, these examples are quite easy to prove. K11T, which is just a book of triangles, and then K12T. So, sorry, this is a book of triangles, and K11T are, okay, sorry. This is a book of triangles, and K12T are a book of diamonds. Okay. So these are common, so it's not hard to prove. And every K1ST is also common by the theorem by Sidorenko. So this is exactly the theorem I didn't mention. So what Sidorenko proved is actually you can add an apex vertex to a Sidorenko graph, which means a bipartite graph that satisfies his conjecture. An apex vertex means I put one vertex that's adjacent to every vertex on the bipartite graph. Then I obtain a common graph. In particular, because KST is common, K1ST is common too. So here's a question. Is every KRST, the complete tripartite graph, is common? So we believe that the answer is yes. But so far, because of the subtlety of the rational function, we haven't seen a way to prove this question. Okay, so this is pretty much for the complete tripartite graphs. And let me move on to the third topic. So let's say so here's my fish again, and here's a tree. And say this is the vertex u and this is vertex v. Then my product is defined as follows. I just glue them together, which means I give a pendant tree to my fish. Okay, then what Jagger, Šťovíček, and Thomason proved is given any non-bipartite H, there exists a treaty that breaks the commonality of the graph H, which means if I add this large enough pendant tree T to my graph H, then the graph becomes uncommon. Okay, and this attaching large pendant tree strategy has been a useful tool for more than a decade. So the aforementioned result by Jacob Fox also uses this attaching large tree approach, and so on. There have been lots of these results. And here's our theorem. So given any tree T, we can construct a non-bipartite graph H, which is a triangle tree in particular, that attaching this tree doesn't break the commonality. So this means attaching pendant trees are sometimes okay. Yeah, so there are some graphs that can accommodate this pendant tree whenever my tree is given. So for example, this guy is common, although this graph is known to be uncommon by Sidorenko. And how we prove this is using some randomized algorithm to analyze entropies. Yeah, so this is the inequalities we obtained. So this is a little bit cheating because we are not really counting these in a uniform way, but some sort of biased way and analyze entropies and so on. So this is a little bit lying, but it's essentially some sort of these inequalities. And because these are common, we can easily argue that these graphs are common too. And so on. If my graph gets larger, then I put some large book of triangles here, and then I'm done. Okay, so here, this was our last theorem, I think. So let me just mention some open problems to wrap up. So here are some here's our theorem. And probably the most interesting results in the area, one of the most interesting possible results in the area is a human proof for the 5 will being common. So far, no one has found this human proof. And moreover, this is essentially the only example that's common in this higher chromatic number case. So there's another famous question that asked by these people saying, is there a common graph with unbounded chromatic number? So is there a sequence of common graphs with unbounded chromatic number? Or in other words, there is a common graph with arbitrarily large chromatic number. But this is a hard question because this is the only common graph with chromatic number larger than 3 we know so far. And I kind of believe that it might open up a way to attack this question if we manage to find the human proof for this. And there's a stability question too. So H being common means that this random coloring minimizes the number of monochromatic copies, but the converse is not necessarily true. For example, if my H is a tree, then it's enough to have a regular graph with density half. Or it's even true for triangles too, because these monochromatic triangle counts are exactly corresponds to these monochromatic 2H path counts by Goodman's formula. One can easily argue that it's enough to have a regular graph to guarantee the correct random-like count for monochromatic triangles. But as you've seen, there are other examples like the 4 cycles or the diamonds that gives the fact that the random coloring or random graph G½ is the only minimizer. So this is another question that one can mess around. And for the second or third theorem of ours, here's a question. So we do know that for some non-bipartite graphs, especially for some triangle trees, a tree can be accommodated. Okay, and on the other hand, we do know that the tree cannot be too large. So the question is how large the pendant tree should be to break the commonality of the given graph. So here are some examples. So what Jacob proved is for KTTT, the complete tripartite graph. So we don't know that this is common or not, but let's assume that it's common due to, by assuming our conjecture on the complete tripartite graphs. And then what he proved is attaching this some constant times t square sized tree breaks the commonality, which means this is essentially linear because t square is roughly the number of edges in the complete tripartite graph. And what Jagger, Šťovíček, Thomason obtained for non-bipartite graphs in general is some exponential bound. And our theorem says if H is a suitable triangle edge tree with many edge intersections, then it basically gives us a lower bound that is linear. Yeah, so there's a huge gap between these two general statements, whereas this result by Jacob says for some particular case, it's enough to have a linear size. Okay, so these are the questions, the open questions I would like to mention. And yeah, this is it. Thank you very much.
Okay, so thank you a lot for this talk. And if there are any questions, please either write them in the chat, or you can unmute yourself and you can just pose the question. So maybe one question I would have is to which other structures could you extend this, just the commonality concept? I know that there is something for patterns in groups, but are there any results for hypergraphs, for example?
I think there should be a natural generalization for hypergraphs because all of these tools basically can be applied in a hypergraph setting. And sometimes it's actually easier or useful. Yeah, so I believe that there would be some natural generalization in terms of hypergraphs, but I've never really like carefully written that up.
Mm-hmm. Yeah, I somehow vaguely remember that the Sidorenko's conjecture for hypergraphs, one has to be very careful, or probably is much more limited than in graphs. So
yeah, so Sidorenko's conjecture is not true for hypergraphs. Yeah, even for linear hypergraphs, the straightforward generalization of Sidorenko's conjecture is not true. Yeah.
So are there any? Yeah, I can. Please do ask. So this is your last chance to ask a questions in the recorded part. So please do so if you want. And maybe now also it's a good opportunity to unmute everyone and clap our hands if you wish to thank Joonkyung for the talk. No, unmute.
Okay.